Hi. Well, in this section, we're going to be talking about chapter 3.4. It's kind of the pinnacle chapter out of these last four chapters, and it's finding the rational zeros, or finding the zeros of a polynomial. Okay. Previously, we've discussed how to find the zeros of a polynomial, which is when you have a polynomial f of x, you set it equal to 0, and you solve for the values of x that make this polynomial equal to 0. We've discussed it and solved for polynomial equations of this form and of this form. And we've also discussed, so these are the general equations of the trinomial and binomial. We've also discussed some that are not trinomials in some special cases, like if you have some x to the fourth plus b squared, how to solve that one, etc. But they're all special cases of a trinomial or some simpler form that we've done before, just some modifications. In here, we're trying to discover how to find all the zeros of a polynomial that's a little bit more advanced. So we're looking for a general theorem. So we're having some polynomial of this form. So this is general polynomial. And we want to know, can we find all the zeros of this generalized polynomial? And unfortunately, the answer is no, we can't. There isn't a advanced quadratic equation that you can solve this for all the zeros. So that being said, though, we do have a few things that we can do. And the first thing we're going to look at is we might not have a way to solve generalized formula for this, but we can find all the rational zeros. So previously, we've discussed different types of zeros that a polynomial can have. They can have rationals, right? Rational zeros, which are numbers like 1/2, 3, -2, 5/2, 1/3. These are all rationals. We also have reals. Now, I know rationals are reals as well, but what we mean here is numbers like square root of 2, square root of 3, pi, right? And we have complex. Complex are like 2 plus 3i, square root of 3i, etc. Now, rationals, all rational numbers are real numbers, and all real numbers are complex numbers. But just to differentiate here, when we're talking about rational zeros, this is what we're talking about. Now, so how can we discover this? Well, how can we work this out? Well, we have a theorem. It's called the rational zero theorem. And what this theorem states is, given some generalized polynomial, like given above, right, that given this generalized polynomial, if we want to discover how many rational zeros this polynomial has, all we have to look at is our leading coefficient and our constant term. All the stuff in between, if we're just trying to figure out the possibilities for rational zeros, are unimportant. Okay, and what this states is if you have some rational zero, some p over q, this is a solution to this equation. It can be found by p equals some factor of a0 and q equals some factor of an. So what it simply states is that if there is a rational zero, it is just going to be some factor of the constant term divided by some factor of the leading coefficient. So an example, example 1. Let's say we want to figure out all possible rational zeros of the function f of x equals x cubed plus 2x squared minus 3x minus 6. Now, I know in this one we could factor this directly. This is one of those special cases that we could do factor by grouping on this and work it out. But let's say we can't do that, or we didn't know we could do that. And we wanted to use this rational zero theorem. Well, all it states is if there is a rational zero, it is going to be composed of some factor of 6 and some factor of 1. So it's going to be some factor of 6 over some factor of 1. Okay, so what are all the factors for P? All possibilities for P are factors of 6, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Remember that negatives 6 can be factored into negative 1 and negative 6. So you have the negative factors as well as the positive factors. And then a factor of 1 for the Q, well, that's just the only thing 1 factors into is another either positive 1 or negative 1. So then to find possible solutions, P over Q is going to be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, or plus or minus 6 over 1, which is just, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So we have 8 possibilities of possible rational solutions. 1, 2, 3, 6, negative 1, negative 2, negative 3, and negative 6. Now at this point, if we wanted to figure out which one of these 4, or if any, like it's possible none of them would work, all this theorem is stating is if it does have a rational zero, it has to be one of these 8 numbers. What we do is we'd have to divide them into the original, or you'd plug them in. So you'd either do, if you wanted, what's f of 1? Let's say we wanted to see if positive 1 was a solution. Well, we plug 1 in to the original up here. So it would be 1 cubed plus 5 times 1, or no, 2. This is 2. 2 times 1 minus, and this is 1 squared, 3 times 1 minus 6. And we work this out. You get 1 plus 2, my bad, minus 3 minus 6. This does not equal 0. So we know 1 is not a solution. And we try negative 1, f of negative 1. If negative 1 works, you do negative 1 cubed plus 2 times negative 1 squared minus 3 times negative 1 minus 6, which is negative 1, negative positive 2, positive 3, negative 6, which again does not equal 0. So then we continued on the road and we find f of 2. Does f of 2 work? Well, it'll be 2 cubed plus 2 times 2 squared minus 3 times 2 minus 6. 8 plus 8 minus 6 again does not equal 0. So f of 2 doesn't work. And then we try f of negative 2. This would equal negative 2 to the third plus 2 times negative 2 squared minus 3 times negative 2 minus 6. So this would be negative 8, positive 6, negative 6. And we find out they do equal 0. So we found our first rational factor. And what it states is negative 2 is a 0. Which means it's a solution of this equation x plus c equals 0. So if we want to put it in the factor form, negative 2 being a solution would be the same thing as x plus 2 being a factor. because remember, x plus 2 equals 0, subtract 2, x equals -2. So this is what we solved for. If we want to go back to this form here, you have to change the sign. Okay, and then we could continue trying the rest, but you get the idea. Okay, so let's do another example. And this one I'm just going to find all possible solutions. I won't test to see which ones work. So let's find all possible rational zeros of this equation. 2x cubed plus 5x squared minus 7x plus 10. Now again, our p is going to be all the factors of 10, and q is going to be all the factors of 2. So p, the factors of 10 are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Factors of q are plus or minus 1 and plus or minus 2. So p over q, possible solutions to this are just these. So plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus the same thing with the 2 on the bottom, plus or minus 1/2, plus or minus 2 over 2, which this guy I'm going to discard because the 2's cancel and it's just equivalent to this one up here, so we don't need to repeat. And then plus or minus 5 over 2, that's good, it's different. And then plus or minus 10 over 2, which this is 5, which we already have stated, so we'll cross that one out. So our possible rational solutions to this polynomial equation are plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 1/2, and plus or minus 5/2. Now at this point, you could either plug them in and figure out which one of these 12 numbers work, and it's possible none of them do. Or you could do your long division, or you could do synthetic division. And that's how you continue this. So this is called the rational zero theorem. Now we will do another example of this later on. But before we continue, let's talk about another property. Okay, let's suppose we want to know how many possible solutions are there. We've noticed that if we have some equation, some polynomial, say 4x to the 5th minus 7x to the 4th plus 5x squared minus 10. This is some polynomial. We know it's a 5th degree because 5 is the highest power. And we want to know how many possible solutions there are. Well, the properties of polynomials state that there are, one, there is as many solutions there are at most in solutions, let's erase this, in rational solutions in a nth degree polynomial. Okay, so there are at most n rational solutions in an nth degree polynomial. There is one more property of polynomials that's useful, and that is if we have a complex solution. If we have a complex solution, and remember complex solutions came up in the quadratic equation. when we're dealing with a quadratic equation, we could get complex solutions to a trinomial. And basically from that, you can, every polynomial higher than x equals 1, or higher than the first degree, can have complex. And even first degree can have complex, because you can always have 2x plus 5 equals 0, and the solution to this, well, no, you can't. Never mind. It's got to be greater than 1. It's got to be 2. So if we have a complex solution, so say we have a plus bi as a solution, then a minus bi is also a solution. Okay? And the reason for this is our polynomials, when you look at them at the very beginning, they have no imaginary parts. They're all real. So if one of the factors has an imaginary part, it must cancel with another part that's imaginary, so that when you're done multiplying them out, you don't have imaginary parts to your polynomial. And the only way that occurs is if you have complex conjugates, and we talked about this when we talked about complex numbers, is a plus bi and a minus bi are complex conjugates, because when you multiply them together, when you multiply those two together, you get only real solutions. Okay? And so what this states, property number 2, is if you do have a complex solution where b does not equal 0, here b cannot equal 0, then you're going to have these conjugate pairs. So it simply states if you have these complex solutions that have an actual imaginary part, they come in pairs. They come in complex pairs. Okay? So there's 2 properties. Now, before we continue on this, let's talk briefly about what a complex number is. When I say complex number, what do I mean? Well, it's really context specific. When I'm mostly talking about complex numbers, I'm doing something like 4 plus 3i or negative I, or square root of 5i, something like that. But remember that complex numbers are anything of this form, a plus bi, and b could equal 0, in which case it could be anything. And remember, both a and b are reals. So real numbers, all the reals are elements of the complex numbers. Okay, so any real number, so the reals is a subset of complex numbers. Okay, so any real number is also complex. So, which this is important to remember. So even 2 is a complex number. Okay, it is 2 plus 0i. Because when it comes to the next theorem, and this is called the fundamental theorem of algebra. It states that if you have a poly f of x of degree greater than 1, then there is at least one complex solution to f of x equals 0. Now, this might not seem very powerful to be called the fundamental theorem of algebra, but it is really powerful when you think about what it's saying. It's basically saying that if you have any polynomial of any degree, it has at least one solution, complex solution, one solution where x plus a plus bi is a factor of this polynomial. could be x plus 2. Could also be x plus 4 minus I. Could be x plus square root 3. Could be x minus pi. These are all complex numbers. I know that some of these are also real numbers and some of them are also rational numbers, but they're all complex. So what's this saying is that we can take in any polynomial, we can at least find one factor. Thing is once you factor a polynomial, once you divide a polynomial by a single factor, you're going to get, when you factor it out, you're going to get another polynomial. Okay, so when we factor out this complex 0, we're going to have another polynomial. Well, then we can reuse the fundamental theorem of algebra and solve that polynomial, because this theorem guarantees that that polynomial also has a complex solution, and hence keep on going all the way till we have nothing left but factors. And by doing this, we can then answer a couple questions. Number one, a nth degree polynomial will have n factors. And what I mean by factors, these could be complex. They are complex, okay? Complex factors. And they might not be unique. Okay? So, what I'm saying here is you could have like, right, we already know what this factors into. Okay, this is a second degree. From this theorem, we can basically get, it's going to have two complex factors. Well, here the two factors are, because 2 is a complex number. But they're not unique. So you can't have repeats. So given that you can't have repeats, but at most you'll have n repeats if you have an n degree. You can't have more than n repeats. All of the factors, including the repeats, when you add them up, they'll add up to n. Okay? That's a strong thing. It allows us to do something else. It allows us to do what's called a linear factorization. From this, we can get that any poly can be written like this. Dot, dot, dot. Okay, where you have these n unique complex factors. And of course, these complex numbers could be real numbers or could also be complex. Okay, and this is called linear factorization. So let's do another example here, and then I'm going to go back and do some more problems, basic problems. In this example, they're going to ask you find a fourth degree poly that has factors of +2, -2, and I. Now, since it's fourth degree, since it's a fourth degree poly, we know that it's going to have 4 factors. So it can be written linearized like this. And we have C1. C1 is going to be 2. This will be a -2, and this will be an I. Well, can we find C4? We can. They haven't given us it directly, but they sort of have. In that, in the previous theorem, it stated if we had any imaginary solutions, complex numbers that have an imaginary part, they have to have their conjugate. Well, the conjugate of I is negative I. So then we know negative I is also a solution. So then we know that this would be our solution. The only thing we're left wondering is an. An could be any real number. And so if we wanted to find a fourth degree that fits these, we could just throw in an an, say 4. Okay. And then if we wanted this, instead of it written on its linearized factorization form, if we wanted it in the standard form, we'd have to multiply it out. I'd suggest multiplying the complex, the imaginary parts together, and these parts together, and then combine them. The whole reason we had to do the conjugate is because we need something that when multiplied equals a real. If we multiply these out, you'll end up with x squared plus 1. Here, you'll end up with x squared minus 4. Of course, we have a 4 over here. Then you'd have to FOIL this out. So this times this is x to the 4th. This times that is 1x squared. Negative 4 times that is negative 4x squared. Negative 4 times 1 is negative 4. And then all we're left to doing is taking your an and multiplying it through everything. And there would be our same polynomial in standard form. Okay. One more theorem here, and then a bunch of examples. The last theorem in this chapter is called Descartes' rule of signs. And this one is a little bit complex, so I'll try to explain it as best as I can. And the first thing before we get into this theorem is we need to talk about what a sign change is. Let's say we have some polynomial. And we want to talk about a sign change. Here, this is positive, this is negative, so there's a sign change there. From here, negative, negative, no sign change, but here to here, there is one. Here to here, there's none, but here to here, there is one. So there's three sign changes. And what Descartes' theorem is going to do is it's going to count up these sign changes. It's going to make a rule for how many real zero solutions you can have looking at these sign changes. Okay. And so what the theorem states is, 1, if you want to find the number of positive zeros, positive real zeros, then find the number of sign changes of f of x. So in the above example, there's 3 sign changes of f of x. So then there is a number, you can have a max of of the number of changes, max. So in the example above, it changed 3 times. So you can have a max of 3 positive reals. Now, we can do a little bit better than this by combining this with another rule. Remember, if there isn't real solutions, then there are going to be complex solutions, imaginary solutions, and those always come in pairs. So we'll either have 3 solutions or 1 solution, because you have to have paired imaginary solutions. So you subtract out the number of pairs. So these are the number of possible positive reals. We either have 3 or 1. Now, for negative reals, the rule states if you're trying to find of negative reals, you count the sign changes of f of negative x. So you're going to plug negative x into the function and figure out the sign changes. So above, so originally we had 3x to the 7th. Let me see, negative 2x to the 5th, negative x to the 4th, plus 7x squared, and then plus an x minus 3. So that was our original one, and we had, so now we're going to plug in what's f of negative x. Well, it's going to replace negative x in here, and what it's going to do is it's going to change all the signs of the odd powered. Okay, so 7, this is odd. So this is going to become a negative 3x to the 7th, because when you plug negative x into x to the 7th, you'll get 7 negative x's, which when you multiply them out, you'll have a negative. Same with this guy. This is odd, so it's going to change the sign. It's going to become a positive 2x to the 5th. This guy will not change because this is an even, so this will just be negative x to the 4th. This guy will also not change. This guy will change because it's odd. And then the constant just remains the same. Okay, and then we count up the sign changes. 1, 2, 3, 4. So in this one, we have 4 sign changes. So then we have a max of 4 negative real solutions. Okay. Now we can do a little bit better because we're not going to have 3. You can have 4, and then you can have 2 less than that, which is 2, and you can have 2 less than that, which is 0. So these are your possible negative real solutions. Because remember, if they're not reals, they're going to be complex, which always come in pairs. So you can't have 3. You can't go from 4 to 3. You got to go from 4 to 2, and then from 2 to 0. So this is the number of possible negative reals. Now, how does this come in? How does this help us? Okay. Well, let's look at an example. How does Descartes' theorem help us? Let's say we have this guy here, okay? And we want to completely factor it, okay? We want to even find if we can, which don't know if we necessarily can, but if we can, we want to even find imaginary solutions if there are any. We want to find all possible solutions of 0. Now, we know off the bat that there's going to be 3 solutions because it's the third degree. And we're going to start with the we're going to start with Descartes' theorem this time. Okay, and look, does f of x, does that have any changes? Has no changes in sign. So what does that tell us? That means there's no positive real solutions. Okay? And this will help us because when we use our P and Q, that means we can completely eliminate the positive possible solutions. We don't even have to check them. Now let's look at f of negative x. F of negative x, well, plug that in. That'll change. This will be negative x cubed plus 2x squared minus 5x plus 4. That's 1, 2, 3. So we can have 3 possible negative solutions. Or if we don't have 3, we're going to have negative real solutions. We'll have 1 because that's 2 less than 3. So we'll either have 3 negative real solutions or 1 negative real solution. Okay, now let's look at our P and Q. Well, back to the original one, it's 4 and 1. So P equals plus or minus 1, plus or minus 2, and plus or minus 4. Q is just your 1. So what's our possible P over Q? Possible solutions are positive negative 1, positive negative 2, positive negative 4. Now we can discard the negatives, or the positives I meant, because Descartes' theorem states that there are no positive real solutions. So we have these, okay? Now let's check them out. In order to do that, let's do long division. I'm going to divide to see if it works out this time instead of doing it the other way. I'm going to divide. That's a 1, 2, 5, and 4. 1, 2, 5, and 4. Okay, divide this out using synthetic division. So you bring down the 1, then you take the negative 1 times this 1 to get negative 1. Add these together to get 1. Then negative 1 times 1 is negative 1, which is 4. Negative 1 times 4 is negative 4, which is 0. So we know this is a solution. And the reason I did it this way is because when this will give us a factor. So we have x plus 1 and then x squared plus x plus 4. Okay? Now we could try the other numbers, negative 2 and negative 4. But since this is already quadratic, I am going to go ahead and use the quadratic equation, since that's one of the tools in our belt, because I'm pretty confident that negative 2 and negative 4 aren't going to work. I'm pretty sure this has imaginary solutions, which the quadratic equation will give it to us. So I'm going to go ahead and do that. So I'm going to solve this. A equals 1, B equals 1, and C equals 4. Okay, we plug it in. Negative 1 plus or minus 1 minus 4 minus, it's positive 1 times 4 over 2 times 1. So it's negative 1 plus or minus negative 15 over 2. Notice this is a negative value right here. Highlight this. This is negative, which means we have two imaginary solutions. So what's our imaginary solutions? Negative 1/2 plus or minus square root of 15 over 2i. Okay, so what are our solutions? Our zeros are negative 1 and then negative 1/2 plus square root of 15 over 2i and then negative 1/2 minus square root of 15 2 over I. And we have found all the zeros for this. We've also find the factor. If you wanted to put it in factorized form, be x plus 1 times x minus negative 1/2 plus square root of 15 over 2I times x minus negative 1/2 minus square root of 15 over 2I. Okay, and there it's factored. Okay. Okay, so that's this chapter. If you have any questions, feel free to email me. The emails are kind of responding slow with everyone on the internet. I noticed someone, I don't know if it was your guys' course or one of the other courses, emailed me, and I didn't get it for like 5 or 6 hours, judging from when the timestamp was. So just be aware of that. Feel free to contact me if you need to set up a video log and you want to chat using Zoom. Just send me an email, but try to give me a day because of how the emails are going and to set something up. But I'd be willing to set something up for you recurringly if you need it. You guys have a good time. Be safe. Talk to you later. Bye.